This is almost our last presentation for this course. The topic today is digital elevation models, or DEMs. A DEM is a digital representation of topography. Topography meaning the shape of the Earth's surface in a particular location. A digital elevation model is a raster data set, and in this raster data set, a cell-based data set, a single value is assigned to each cell, and that value is the elevation of the data set. This is a simple example of a digital elevation model for a study area that's only 5 cells by 5 cells. The value of each cell is the elevation. The lowest elevation in this study area is right here because it has the lowest value, and the highest elevation is up here. So in this case, water, for instance, would flow roughly in this direction. Ooh, I think it would go along the side here, the way this one is set up. But that's the essence of a DEM. It's really a very simple data structure. It is a raster data structure, as I said. In this case, each of the values is represented by a certain color to make it more visualizable. And as in any raster data structure, each of the cells represents the position in some coordinate system. In this case, it's a simple XY system. In GIS, it might be a UTM system, where the origin is the intersection of the equator and the prime meridian, for instance. Digital elevation data can be displayed in a variety of ways, and that's one thing that we like to have a GIS for, is that these data sets, which are just masses of numbers in a grid format, can be translated. They can be shown as a wire mesh, shown as a 3D view, or even a 3D view with topographic information besides elevation actually overlain on top of it, and we'll see how to do that. Another example of a digital elevation model in which we actually have a 3D view and a color set for the various elevations. There we have discrete categories of elevations, and we also have shown here a contour, a line of equal elevation, just a way to represent a digital elevation data set. Another example in this picture here, this is highly detailed data which was collected with a technology called LiDAR, and it's actually possible to see buildings with steep sides, pine trees, and even a church with a steeple in this position. More representations of digital elevation data, again as a 3D or a wire mesh, converted back into contours, which are more familiar ways to look at an elevation. GIS has several extensions which are able to work with digital elevation data. One of them is called Spatial Analyst, which we will make good use of in this week's exercise, plus some more sophisticated computational methods such as 3D Analyst. Many of these things are over time, these two packages of operations are kind of merging together. Eventually there'll be just one extension to deal with digital elevation models. There's a lot of computation and operations that are available to use with a digital elevation model. One of them is to actually go backwards and convert a DEM in digital GIS format back into a contour data set, which is more familiar for those of you who've used USGS topographic map. So you can go backwards to contours. It's very possible and frequently done to compute slopes from a digital elevation model. And it's a simple operation inside a spatial analyst to start with an elevation data set and compute it out to a slope data set. In this case, greens are flatter slopes and reds are higher slopes. One small warning using slope is that it does allow you to calculate slope using two different representations of slope. One is the degrees that a slope is, and the other is the percent that the slope is. Percent defined by rise over run times 100, and degrees defined by the angle of the slope here. And at small slopes, the degree of slope and the percent slope are very similar, but at larger slopes they start to deviate. For instance, at a steep slope such as this, it's a 45-degree angle, but a 100% slope. The rise is the same as the run in this case, and for very steep slopes, the percent slope gets very large. So there is a distinction between degree of slope and percent of slope that does need to be considered. There's one other thing in elevations and using DEMs, and that is many operations have something called a Z factor, which is a vertical exaggeration. And there's really two purposes for a Z factor. One of them is if the elevation units are in different units than the XY units. So we might have a UTM coordinate system where the X direction and the Y direction are measured in meters, but our elevation is in feet. In order for computations to come out correctly, we have to apply a Z factor of 3.048, just from memory, to convert feet to meters. And that would be a division by 3.048, or 3, and that should be looked up. Don't take my word for that one. But that another way that a Z factor can be useful is it can provide a vertical exaggeration in things that are in visualizations, because even mountainous areas are relatively flat compared with the size of a large area or the surface of the Earth. So in order to see them really clearly, exaggerating in the vertical direction makes some sense. It's also possible with a DEM to calculate something called aspect, which is the direction that the slope faces. And it actually does make a tremendous difference whether a slope is south-facing or north-facing, for instance, depending on the sun angles that it causes, etc. So aspect is a useful tool as well. Another tool that we'll use is something called Hillshade, which takes a digital elevation model and makes a pseudo 3D representation for very nice viewing, such as on the left, where I actually have a hillshade and coloring draped over it and a stream network, which shows a very nice representation of the Earth's surface. It's possible within a hillshade to actually be omnipotent and control where the sun is. Different angles of the sun will produce different reflections, so to speak, in the pseudo 3D and make the topography look different. So one can control the sun angle and I think the sun elevation as well, the elevation and the azimuth, where the sun is east to west and where it is up and down in the sky. And this explains this. Azimuth and altitude. Altitude is how high the sun is in the sky. Azimuth is what direction it is on the compass. Your lab exercise will consist mainly of creating an image that looks like this on the right-hand side. The exercise is well laid out, and I'll review it again at the end of this video. Basically what it is you create a hillshade and then put a color image of the DEM on top of it and add some transparency. I'll demo that shortly. Another interesting computation that can be made with DEMs is something called a viewshed analysis. And this is an analysis that allows one to compute what areas are viewable from a particular point, and conversely, what areas can see that point. So here's a landscape with certain elevations. Here's a point of interest, and this is the computation of what areas in the landscape can see this point, or what areas a person at this point can see. These are useful for things like computing cell tower locations, because cell tower and cellular signals depend on line of sight to make a transmission. They don't go through the Earth's surface very well or cut through hills hardly at all. Also, windmills are another example of where this computation might be made, and it's nice to know in advance what people will have their scenery changed by the installation of a windmill at a particular location. There are lots of places to get digital elevation model. At the global scale, there's a package called, or a set of data called GTOPO, which is very, very crude. Each cell is approximately 1 kilometer in size. So if you're doing something that's country size or continental size, this would be appropriate. For a smaller study area, this is just too crude. There's also another data set called the Shuttle Radar Topography Mission, in which a LiDAR laser type elevation collection instrument was put up into a space shuttle, and the whole Earth's surface was mapped at 90 feet 90 feet resolution, and better. I went ahead too far. Excuse me. And actually, the Shuttle Radar Topography Mission has been reprocessed, and now for most of the Earth it's possible to have 30-meter cell sizes, which is very good. SRTM, there are better data sets available for common places like Monroe County, New York, but if you're looking at exotic places, the SRTM may still be the best available elevation data. GTOPO, this is an information slide about GTOPO for your just for reference for the future. The SRTM, here's more information about it. The 30-meter has been achieved and is available to the public for the whole, just about the whole planet, I believe, and some references as well, and one other site with information about digital elevation models. This was rather quick, but DEMs are something that we'll be covering more thoroughly in the second semester course, and all I needed to do for this semester was a brief introduction to them and have you the feel of them. And the best place to get digital elevation data is from the National Map Viewer, which we've looked at before and which I'll give a brief demo of right now. Let's see here. There's my National Map Viewer, and I followed the same process for National Map Viewer as we've used before, in which you start the program, you zoom to the location you want, you say download my current map extent, and then you say I'd like elevation data. So we've done that before. It's relatively straightforward, except for the fact that there's a pretty large number of different DEM data sets to choose from, and there's several ways we can choose by the resolution, the format, and the resolution and the format are the most significant. If you're going to do data, you always want to get the data with the best resolution or the smallest cell size. 1 arc second is about 30 meters. 1/3 of an arc second is about 10 meters. People normally don't talk about distances or cell sizes in arc seconds, but it is a measure of distance, so it can define a cell size. 1 arc second is rougher in quality than 1/3 arc second. So we'll look at 1/3 arc second, and then 100 meter or 200 or 300. I don't see a 300 for this data set, are obviously much cruder and not anywhere as near as useful, unless you're looking at like the whole state of Alaska, for instance. It's also better to get an arc grid format. It's the most universally applicable and works best in arc map. So what we want is to find the smallest value of resolution in the arc grid format, and I think there's our winner right there. So the data set that we would choose in this case is that one. And the reason that you see two of them that look the same is the study area that I have that I've chosen overlaps two different data sets. So in order to cover this area completely, you'd need to have two different. That's because we're right at the edge of the 77 to 78 longitude. So there would be two data sets required in order to cover this small study area. And that's all I have to say about that. I'd like to squeeze into this a demonstration of the lab that you're going to do, just to make it as clear and as easy as possible. The lab uses two data sets. One of them is a digital elevation model for Mount Marcy, and the other one is a map of the streams in the Mount Marcy quadrangle. And I'm going to see if I can track those down. And the Mount Marcy DEM is called Mount Marcy DEM, and streams are called Mount Marcy Hydro. I'm going to warn you about loading a DEM. It's easy to have a bit of a problem with it. I see this; it's in a folder, so I can open the folder. But now I can see here the grid, and I shouldn't break that down anymore, or else it will confuse. So I don't want to climb any deeper into those folders if I need to do a connect to folder or anything. That's what and there's the DEM right there. I want to demonstrate that again. If I needed to make the point that I was just trying to make, and my computer was set up not to show you that point, if I need to do a connect to folder and I want to connect to a folder that contains a DEM, I would first choose my desktop, then choose the course folder, and inside of that is my Mount Marcy DEM. What I don't want to do at this point, it's not going to let me, so it's very convenient. It's not going to let me go any deeper into this folder, because once you get into this folder, you get into subfolders that aren't meaningful to Windows or to a person. So I should just leave my connect to folder at the level of the folder that contains the DEM. I don't want to dig any deeper into the folders, or it won't be meaningful anymore. Anyway, that was just confusing. But you may or may not see that in the computer that you work on. So there's my digital elevation model. The steps you're going to go through are relatively simple. The first one is to turn this black and white image into something more familiar to the eye. In fact, using the same palette that National Geographic uses for its mapping, and that is to go right-click on this, then go to Properties and ask for Symbology, just as we've done several times before. And under Symbology, I can go ahead and pick a palette that I want. The one that I want it by name, not just by vision, so I can actually right-hand click on this little arrow here, and it says, and I turn off graphic view, and now it gives me names, and I can pick a palette by a name, and the one that I want is Elevation Number 1, which is the one that's most familiar to the general public and probably to you. And I just say OK, and there's Mount Marcy, and there's I forgot what all the features are now because I haven't been there in such a long time, but this is the digital elevation model of in good colors. High values are the white colors, mediums are reddish orangish, lowest are greens and blues in this particular digital elevation model. And that's pretty. The next thing I'm going to do is I'm going to be sure that I've turned on my Spatial Analyst extension, because I'm about to use it. And Spatial Analyst extension is turned on. I got to that by asking for Customize Extensions, and I made sure Spatial Analyst was turned on. Another important little detail, and I think I've already shown this 5 times to my other class, but maybe not to you. The next thing we'd like to do is go to our ARC toolbox one way or another, either up here or down here, and load up the ARC toolbox. It'll be here any second now, I promise. And once within our toolbox, we're going to go to the Spatial Analyst tool group, and we're going to ask for hill shading. And here's Spatial Analyst Tools. And again, this is in the lab write-up, the same steps, but it's just nice if you've seen it before. Then we're going to go to the command or to the subgroup called Surface and ask for Hillshade. And it'll be here momentarily. The input raster is the only one we have. The digital elevation model is the source for this. We're going to let it go anywhere. We don't care. We'll just let it store it anywhere because it's only temporary. I'm going to leave the sun position alone, and I'm going to have an exaggeration of 20. And say OK. And it should only take about a half a minute for this to complete. So it'll load up soon. And once we have a hillshade, the next thing I'm going to do, I believe it's running in background mode right now. So something I can do right now is go back to my table of contents, and I can right-click on this. I'm trying to save time here by there's the hillshade. It's showing up in the crawler. But I'm going to go right ahead and make the properties of my regular DEM. I'm going to make it the display. Let's see. My eye is not catching it. There it is, transparency. Transparency of 60% is a convenient amount, and say OK. And now what's showing on my screen is the hillshade of the Mount Marcy area, and it's quite dramatic, and there's gorges and very deep valleys all mixed in with this. And I've already made my DEM partially transparent, so I'm going to zap it up to the top. So now I'm going to add a color scheme as well to these, and now we can see the mountains really clearly and the valleys clearly. And the last little thing for today's class is, and for the exercise that you're going to hand in, is to add the streams of Mount Marcy right on top of that. And here what I don't want to do here, this streams is in a different data format called, I can't remember what it's called. I just choked on the name of it. But it's an older data format that's actually made up of sub-files, which you don't want to display individually. So what you really want to do is, as soon as you see streams, just say load that. Don't break it down into its component parts. And we'll just say OK. And there's all the streams and drainage networks, and also a few ponds as well. Here's a pond down here. Streams are now red. Of course, we should make them river color. And there's your extremely attractive and impressive topographic map of the Mount Marcy area. What I'd like you to do is now is save this as a PDF. And I just remembered these are highly detailed, and they might make a very large PDF. So when you say export map, which you've been doing to make PDFs, I recommend you reduce the resolution to 100. It'll make the map look slightly grainy, but it'll also create a map that has a size that is tolerable for your Dropbox. And that will be the end of this video. And there's one short video of about 5 minutes to close off the course. Again, in summary, your exercise, which you'll see in the assignment sheet, is to go through the process I just demonstrated and create a PDF that shows this very nice map.